Okay, good evening, everyone. Welcome to O-Level Physics lesson. My name is Mr. Chu. Okay, today is the 1st of March 2022. And we'll be studying and I'll be sharing with you the topic of static electricity. Okay, a show of reaction. How many of you have started learning this topic? Okay, if you have learned this topic, give me a yes reaction. If you have not learned this topic, give me a no reaction. Okay, Yifan, Oscar, Xiaoxing have learned. Ray and Ryan, how about the two of you? How about Ryan? Have you learned this topic already in school? Okay. Everybody have learned this topic except for eating. Okay, don't worry. But y'all think that it's a bit slow, please let me know. Okay, let me show you all the overview of physics. Again, I'd like to show the overview before each lesson, each topic. Okay, so let me share with you the overview. Okay, this is the O-level physics topics that you all need to know. Okay, so for Yiting, her school is at light. Okay, light. Okay, so after light, I think she'll do sound, then she'll start with the electricity and magnetism. Okay, so over the past 1 year till now, we have gone through the blue team, the green team, the yellow team, and so on. Okay, so the final team that we're going to talk about this time round will be this purple team called electricity and magnetism. Okay, one thing I want to share first is these two topic, electricity and magnetism topic, these two topic, they have to be together. Okay, because electricity and magnetism are linked. Okay, I repeat myself again. Electricity and magnetism are linked. In primary school or in lower secondary, they seems very separate. Okay, they seem very separate. Electricity is electricity, current magnetism got to do with magnet. So how are they related? Okay, but what we're going to learn in O-level physics is you're going to understand that electricity and magnetism are actually related. And then these relations will be emphasized in the last two topics, which is I would say, one of the hardest topic in the whole of physics. Okay, electromagnetism and electromagnetic induction. All right, so far? Okay, so far, any question for me regarding my introduction on the theme, okay, on the overview of physics as well as the introduction of the theme? Okay, so you have a big picture where we are. Okay, so when you all continue to learn physics in A-level, a university, you'll all be the same team. Okay, Newtonian mechanics will be the same team, thermal physics the same team. You're not going to learn extra topics. Okay, of course, there are extra topics that's within the team. Okay, but generally, physics will be like this. Okay, don't ignore the measurement. Generally, the physics will be broken down into the Newtonian mechanics, okay, thermal physics, wave, and electricity and magnetism. Okay, basically, this is what physics is about. So when you go to A-level, when you go to university, this will be the topics that you're going to learn. Okay, the same topic. And then when you go A-level, you'll be studying the same thing again. You'll be studying static electricity, but in more detail. You'll be studying circuit, you'll be studying electromagnetic induction, will be in more detail. Okay, there's one theme that is not shown in O-level, will be the theme called quantum physics and relativity. Okay, that one will be extra theme, which you will get introduced in A-level. But other than that, the basics of physics will be these four themes. Is that clear? All right. Okay, so let me introduce what exactly is this theme about. Okay, let me share with you the syllabus. Do you actually read syllabus one? Okay, take about 2 minutes. Read the overview here on top. Okay, read the overview of this theme. Okay, once you are done, give me a thumbs up. Okay, thumbs up, thumbs up. Because some of you put the tick and cross earlier. Okay, Yufan has finished, Ryan finished. Okay, Oscar and Haore, have you finished the 2 paragraphs? Haore, are you okay? All right. So just let me go back to the mind map again. Yiting, if you like the mind map, you just take a screenshot. Okay, that is if you like the mind map. Okay, so what's happening here is this. The introduction says that which I mentioned earlier on, for a long time, we going back to before 1800. Okay, electricity and magnetism are treated as separate. Okay, so for this topic itself, okay, we are going to talk about static electricity. Okay, what is the meaning of static electricity? Meaning that we're talking about charges, electric charges that is not moving. Okay, I repeat, static electricity refers to electric charges that is not moving. Okay, so some example of a static electricity is like when you charge up a balloon, and then when you touch it, you suddenly feel you get shocked. Okay, so that is static electricity. The charges on the balloon are not moving, but because there's a difference in the charges between you and the balloon, there's a motion of the charges, and then you feel electricity going through you. Okay, so that is the topic called static electricity. And then we'll move on to current or electricity, is where the charges. Okay, let me just talk about charges. Hold on for a while. Let me just write here. Okay, so charges we learn. Okay, I don't know whether have you learned this, but charges are basically positive and negative. Okay, so these are charges, and if they are not moving, when these positive and negative charges are not moving, we call them static electricity. Okay, I'm sure you are very familiar with charges because you learn about ions in chemistry a lot. Okay, so positive, negative shouldn't be a problem. Okay, the concept about plus and minus, where there's 2 different sides of a coin, is also found in magnetism. Okay, where there is a north pole and a south pole. Correct? In the magnet, there's a north pole and a south pole. Okay, so for electricity, there's also a positive charge and a negative charge. Okay, so the study of a charge that's not moving is called static electricity. Okay, and then when the charges are moving, then then that is why you see electricity. Okay, and then that's before we learn about current of electricity. And then from there, you will learn about current, you'll learn about potential difference, voltage, resistance, and so on. And then from this knowledge, you will need to know how to create simple circuits based on this knowledge. And then finally, practical electricity is where we learn about like household, how much power of electricity do you use. Okay, so we learn about the power of your electricity. Okay, so this is the brief summary of this theme, electricity and magnetism. Then we talk about magnetism by itself, okay, the North Pole and the South Pole and so on. Then once you learn all this already, okay, so the first 4 here, this is just the introduction to electricity. Then the magnetism is the introduction to magnetism. Okay, once you learn what is electricity, the basic of electricity and the basics of magnetism, the last 2 topic is the tougher one. Okay, so what is electromagnetism? Electromagnetism, you have learned this before in primary school. Okay, electromagnetism is where you use magnet to produce sorry, I'm wrong. I'm so sorry. Okay, electromagnetism is where you are using electricity to produce magnetic effect. Okay, so in primary school, you have learned how to make an electromagnet. So you're actually using an electric current to produce a magnetic field. And this magnetic field is a force that will allow things to move. Okay, so electromagnetism is a very, very important topic if you want to be a scientist or engineer in the future, because all your motto is based on this theory. Is that clear? Okay, so electromagnetism is where you supply electricity and then you produce a magnetic force, and this magnetic force will move. And that's where the motto comes in. Okay, then electromagnetic induction is the opposite. Okay, it's the opposite. Okay, where you are actually using a magnetic field to produce electricity. Okay, what do I mean by that? Okay, to produce a magnetic field, how do you produce a magnetic field? You actually need to move something. So when you move, for example, when you move a magnet, okay, when you move a magnet, so when you're pushing the magnet, you're actually creating a magnetic field, and this magnetic field will actually produce electricity. Okay, so what's the opposite of motor? This is electricity creating motion. Okay, that is because of magnetism. Okay, it's called motor. And what is the process that produces electricity? Because if you don't learn the last topic, you have no such thing called computer. You have no electric power supply. So the last topic is very important, and that because that is how electricity is created. Okay, so generally the last topic we are learning this, and this idea is the basis of how an electric generator is actually based on. Is that clear? You are using like a hand to turn something using a force to create electricity. Okay, so this is the whole overview of this purple theme, the electricity and magnetism. Okay, we are learning the separate part of electricity and magnetism first, and which we're going to tie them together for the last two topics. And then why is it important? Because the last two topics is where you get things like motor and generator. Without generator, you have no electricity. Okay, without motor, you have no fan, you got no car, and so on. Okay, so this is the reason why we learn this topic together. Okay, up to now, if you are clear, give me a thumbs up. Okay, at least you have a big picture of what this theme is about. Xiaoxing, are you there? Are you okay? All right. Okay, so are you clear about the big picture? Did your school share with you the big picture like this? Or they just go into the topic one by one? Can you share something, write something in the chat? Share with me, have you heard of this big idea from your school? Or do you actually read from any of your books? Or you go and Google, go and find out more about this? Okay, at least I'm sharing with you the big picture, so at least you appreciate what you're going to learn. Okay, and then you know that all these are actually linked together. Okay, Yifan say that she did not learn anything like this. How about the rest of you? In school, did your teacher share with you why you are learning these together? Any feedback for me? Only Yifan give me feedback. The rest of you don't like feedback. Okay, let me go back to the syllabus again. Okay, this syllabus you can find in the MOE website or the Singapore Examination Board website. Okay, so the topic that we're going to learn first will be static electricity. Okay, so static electricity, there are 4 subtopics. Okay, first of all, you must know the law of electrostatics. You must know the principle of electrostatics. You need to know what is the electric field, and then what are the useful application, why we learn this topic. What are the useful applications that we can do down here? All right. Okay, so what is the learning outcome? Okay, first of all, the law of electrostatics, you must know that, okay, which I mentioned earlier, you must know about there are positive and negative charges, and then what is their unit. Okay, the second outcome you must know is that unlike charges attract and like charges repel. This one is actually very similar to magnetism. Same idea, instead of pole, you write down charges. Okay, then next, you need to know the third part, the electric field, which is what is electric field? Electric field is a region, okay, where electric charge experience a force. Okay, this statement is very familiar. You have learned this before in an earlier topic. And then where do you actually see this term before? It's called gravitational field. How many of you remember gravitational field? Okay, give me some reaction. Do you remember gravitational field? If you remember, say yes. If you don't remember, say no. It's okay to say no. I'm just trying to tie things together so you all can learn things better. Okay. Then you need to know how to draw the electric field pattern between 2 point charges. This is also very similar to the magnetic pole. Then you must understand how do you actually charge an item by rubbing. Then you create then by creating an electrostatics. Okay, and then why is it charged? Is because there's a transfer of electrons. Okay, I will be going through this with you all. Okay, describe experiment to show electrostatic charging by induction. Describe example where electrostatic charging is actually dangerous. And finally, how is this used in a photocopier? Okay, so this will be what you need to know. Okay, at first sounds very overwhelming, right? But this topic actually don't really come out a lot in exam. Okay, but you need to know this topic because the first topic is electricity. All right, so okay, so maybe let me share with you a few things here first. The simple stuff. Okay, so we know that there are charges. Charges, they are positive and negative. Okay, this is the unit, is in Coulomb. The symbol is capital C. Okay, I hope you are writing notes now. Okay, so charges is measured in Coulomb. Okay, there is a positive and a negative charge. Okay, can all of you go and do me a favor? Can you go and try to find out what does 1 Coulomb means? Okay, I give you 1 to 2 minutes, you go and Google. Okay, what does 1 Coulomb means? Okay, then you type it out in the chat. Share with everyone. Okay, Oscar gave me a correct answer. Well done. Even that is incorrect. Incorrect. But it's okay. Good try. Okay, Oscar and Ethan, can you share your findings with everyone? Okay, share your findings with everyone. Okay, the rest of you, are you going to add on anything else? Okay, so in chemistry, okay, chemistry, can you tell me in chemistry, give me an example of a positive charge? Can you give me an example of a positive charge? Anode. Anode is not positive charge. Anode is, I also can't remember. Okay, Ryan says sodium ion. Correct. You can say positive ion example. Sodium is Na. Sodium is at which one? Plus or is 1 plus or 2 plus? Do you remember? HNACR is Na plus. Okay, so sodium is Na plus. Okay, so this is one charge. So if just one sodium atom, okay, without one electron, that is one charge. Is that clear? Okay, I'm just saying charge, I'm not saying coulomb. Okay, another example will be one proton. One time proton or many proton. Okay, so one proton is also a positive charge. Okay, negative charge. Okay, same thing. You can have chlorine minus, or you can just say electron. Is that clear? Okay, so to measure the charges, we use this thing called coulomb. Okay, you're not going to learn this in chemistry, but I'm going to link them together so at least you appreciate. Okay, so you learn in chemistry. Okay, an atom, for example, helium. Helium has two positive, and then you got two negative, two electron outside. Then in between got two neutral, right? Two neutron. Okay, so each of these plus has a power, has an electric charge. Okay, so we use that. Okay, the unit that we use to actually explain this charge is in coulomb. But 1 coulomb, okay, doesn't mean that it's the charge of 1 plus. Okay, 1 coulomb is not the charge of 1 minus. I repeat again, because Yifan was saying that it's the amount of charge carried by 1 electron or 1 proton. Okay, that is not correct. Okay, so what is 1 coulomb? 1 coulomb is the amount of charge. Let me go and Google. When I say Google means you also don't need to memorize. But I want you to understand what it actually means. Okay, so 1 coulomb is the amount of charge in 6.24 times 10 the power of 18 proton or electron. I repeat, if you put 6.24 times 10 the power of 18 proton together, okay, that will give you a charge of 1 coulomb. I repeat myself again. If you can gather 6.24 times 10 to the power of 18 electron together, okay, the combined charge will be 1 coulomb. Clear so far? If you understand this so far, give me a thumbs up. Okay, but you don't need to memorize this number for now. Okay, maybe at A level, yes. But for now, I just want you to appreciate a lot of electron together will give you 1 coulomb. Okay, so we talk about coulomb. The symbol for coulomb is 1 capital C. Okay, so you don't need to go and spell coulomb all the time. And then for unit that is named after people like Newton, like Pascal, when you spell it out, remember the first letter is small, but usually the symbol is capital. Okay, I repeat again. In a lot of unit where they name after people, right? When you spell the unit, the first letter is small. Okay, but in the symbol, it is capital C. Is that clear? Okay, so another example would be Newton. Okay, when you say that this force this push has a force of 5 Newton, you write down this 5 Newton. You want to spell out, you write down small letter. Okay, when you write down you want to spell out the unit, you write down in small n. But when you write down the symbol, usually it's a big capital. Okay, but if you want to write down the name of Isaac Newton, of course you write down capital N. Did I make myself clear? And this notation is similar for, if I'm not wrong, all the unit that's named after people. Clear so far? Okay, so this number is not very important for O-level physics, but just to give you an understanding. To get 1 coulomb, you need this amount of charges, okay, whether is it a positive charge or negative charge. So positive charge example will be proton. You need 6 times 10 to the power 18 proton to give you a charge of 1 coulomb, or you need 6 times 10 to the power 18 electron to give you a charge of 1 coulomb. Okay. Okay, now I want all of you to go and read the definition that Oscar shared. Okay, the definition that Oscar shared. This definition is also correct. Okay, 1 coulomb is the amount of charge from a current of 1 ampere flowing for 1 second. Okay, can you just read it first? Later I explain to you. Okay, this definition, you will not learn it in this topic. You will learn this in the next topic. Okay, you learn in the next topic. But I want you all to read it. I can explain to you all so that you at least understand what this means. So once you're finished reading Oscar's definition, give me a yes reaction. Okay, give me a yes reaction. Okay, very good. Okay, before I continue, charge itself also have a symbol, just like force. The symbol for force is F. Okay, so F is equal to 5 Newton. So you don't want to spell force, right? You write down F. Okay, this is a symbol. Same thing, charge also has a symbol. The symbol for charge is Q. Clear so far? Okay, so let me explain what does Oscar definition mean. Okay, so I'm going to talk a bit about the next topic. So for example, just imagine this is an electric wire. Okay, electric wire. So we have learned the term called current before in lower sec as well as primary school. Okay, we have learned the word current, and then you also know that current, the unit for current is in ampere. So for example, I give you a unit called 1 ampere. Okay, so what does charge mean in this case? Okay, so 1 coulomb means that, for example, in this wire, if you use a ammeter to measure the current, it gives you a reading of 1 ampere. Is that clear? If we give you a reading of 1 ampere, it means that every second, okay? So let's say you put a counter here, you go and count the number of charges that go through. So 1 charge can be 1 proton or 1 electron. But in electricity, it's electron that's moving. So you go and count, okay, how many electrons moving from left to right at this point of time. Okay, so you count. Okay, you start counting. Every 1 electron go by, you click, 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 click. Okay, so what does 1 coulomb means? It means that if your current is 1 ampere, for that 1 second, you'll be able to count 6 times 10 to the power 18 electron moving past. You have me myself clear? Okay, if you understand, give me a thumbs up. You want me to explain again, give me a no reaction. Harry, are you okay? Ryan, is your camera working? So I repeat myself again. If you use a ammeter to measure the current in your wire, okay, so your current tells you that your current is 1 ampere. It means that if you were to count for 1 second, how many electrons go by in the 1 second? And if it's 1 ampere, it means that there is 6 times 10 to the power 18 electron going by in 1 second. Okay, that's the meaning of 1 coulomb. Okay, so this is the definition that you're going to learn in the next topic. Okay, so what does it mean is if your current is 1 ampere, there will be 6 times 10 to the power 18 electron moving past in 1 second. Okay, if you were to count in 2 seconds, how many people run past you in the wire in 2 seconds? You'll be 2 coulomb. Is that clear? The current is 1 ampere, but 2 seconds, you'll be able to count 2 coulomb of charges going by you. 2 coulomb will be 2 times this value. Okay, so as a revision, I'm going to blank out this whole page. I'm going to ask you a question. Okay, and this question, I want you to also write down as a note because I want you to remember. Okay, remember. I hope that from my explanation, you can remember better. My first quiz for you, what is the symbol of charge? Okay, all of you write it down and send to me. What is the symbol of charge? Okay, Yuting, well done. Qiaoxing, well done. Qiaoxing, incorrect. Yifan, incorrect. Oscar, well done. Yifan and Qiaoxing, try again. What is the symbol of charge? Qiaoxing, well done. Ryan, are you there? How are you there? Yifan, very good. Ryan and Howry, where is both your answer? Okay, since you are not interested, then I'm going to move on. Howry, incorrect. Yeah? You're not listening. The symbol for charge is Q. Okay, the symbol for charge is Q. Okay, my next question. What is the symbol for Coulomb? The symbol for Coulomb. Okay, all of you type it out now. Well done, Yuting. Howry, your letter is correct, but your size is wrong. Qiaoxing, well done. Yifan, well done. Oscar, incorrect. It's not small. It's not small. Okay, Oscar, well done. Okay, no more answer. Okay, so the symbol for Coulomb is a capital C. Is that clear? Okay, and let me just add on. This is not in this topic, but let me just talk a bit about this topic. I mentioned before in a wire, okay, 1 coulomb of charge, okay, 1 coulomb of charge is the amount of charges. In this case, electron. Okay, wait. Electron, let me write another way. You all learned this before in chemistry, right? It's the number of electron, but you don't use number of electron. You know that 1 coulomb of charge means same as 6 times 10 to the power 18 electron. Okay, it's 1 coulomb of charge means 6 times 10 to the power 18 electron. So 1 coulomb of charge means this amount of electron moving through the wire in 1 second. If the current is the formula, the symbol for current is 1. The symbol for ampere is 1A. Okay, in 1 second. Okay, so if your current is 1 ampere, so in 1 second, there will be 1 coulomb of charge moving through. All right. If your current is 2 ampere, so 1 second, you will get 2 coulomb of charge. Understand so far? If you have 1 ampere and then you measure 2 seconds, you'll get 2 coulomb of charge moving through here. Okay, so having known this, how to tie in current and charge based on this definition. All of you, okay, Oscar, can you copy and paste the definition again? So based on this definition, how do you link charge and current together in a formula? Okay, look at what Oscar said. Based on what I explained so far, I give you 3 variables. One is the current. Second is the charge. Okay, another one is the time. So 3. So based on this definition, can you come up with one formula? Okay, come up with one formula based on Q, I, and T. Okay, so after my explanation, and then all of you look at Oscar's definition, can you form a formula based on Q, I, and T? If you need help, type help in the chat. I'll give another example for you. Oscar, well done. Okay, so based on this explanation, and then based on these 3 quantity, can you form an equation? Qiaoxing, well done. Who else? Yuting, well done. Very good. How about Ryan and Hao Rui? Hao Rui, well done. Ryan, how about you? And Ethan, how about you? Ryan, Ethan, are you able to come up with a formula linking these three? Okay, Ryan, well done. How about Ethan? Okay, so if you understand the idea of how charge and current are linked, you really need to memorize the formula of current and charge. Okay, you understand where I'm coming from? I'm trying to make you appreciate the formula. Okay, and the formula that most of you tell me is like this. Current is the amount of charge divided by the amount of time. Okay, it's how much charge there is per second. Is that correct? How many charge are there moving through the wire in each second? So Q over T. Okay, some of you also tell me, you rearrange, you give me the formula like this. Okay, charge is the number of, is the product of the current multiplied by the amount of time you need to count. Okay, so these two, does it make sense now? These two formula, after I explain the meaning of charge. Is it helpful? Then for me, how do I memorize the formula? My school teacher in the past teach me like this. So if you think it's helpful, you can also learn the same thing. They make us memorize this formula and then just remember this. Q is it. Okay, Q is it. Is the equal. Then this is the it. You know the it? The English word it. Okay, so for me, if I really cannot remember the definition, the idea, what's the meaning of current, what's the meaning of charge, how are they related, I just remember Q is it. Okay, so far it is helpful for you. Okay, if this is helpful, give me a yes reaction. If you think this is not important, give me a no reaction. Okay, I got 2 persons say not useful, but the rest say useful. Don't worry. Okay, let me go to the next one. B. Unlike charges attract and like charges repel. This one I will not touch much. What I'm going to touch on is how is it similar to other topics that you have learned before. Okay, so I'm not going to touch much about this. Okay, so all of you have learned before. Like always repel, unlike always attract. Correct? So this is called for static electricity. You apply the same thing to magnetism. Okay, so I do not want you to remember 2 different things. Just remember the same thing. Unlike pole attract and like pole repel. That's all. Is that clear? Okay, so they are linked, they are the same. Okay, just remember that for electricity and magnetism, instead of the word charge, you change to pole. Okay, so example will be 2 charges. If they are the same, it's called like charges. If they are different, they are called like charges. They will repel. Okay? But if you put like charges, unlike charges together, they will attract. Okay, this one, I don't think I need to explain much. Okay, the key point I want to touch on is, it is the same as magnetism. You just replace the word charge with pole. That's all. Okay, if you are clear, give me a thumbs up. Okay, if you are clear, give me a thumbs up. Chelsea, are you okay? All right. Okay, can you clear all your reaction? Clear all your reaction. Clear all your reaction. Because I can't clear your reaction. Okay, next thing. Part C. Okay. Part C, I'm also going to share the same thing. In Newtonian physics. Okay, in Newtonian physics, where we learn about the forces, gravity, and so on, right? We have learned this thing called gravitational field. Okay, we have learned gravitational field. We have also learned gravitational field strength. Okay, so G equal to 10 Newton per kg. this G is called gravitational field strength. Okay, just a revision. Okay, just a revision. Okay, so this is not, this G is not gravitational field. This G is gravitational field strength. Okay, just a revision for you. Okay, so I'm going to talk about gravitational field without the word strength. Okay, so likewise here, gravitational field. Okay, so you have learned this before in the earlier topic. It's the same thing. All your electric word change to gravitational, or all your gravitational word change to electric. Okay, so if you learn, if you remember, okay, when you learn this in the mass rate density topic, gravitational field is a region in which, in this case, not a gravitational charge. Okay, in this case, the word here is when a mass experience a force. Do you remember? Okay, gravitational field is a region where a mass, okay, experience a force. Okay, so now today you're going to learn electric field. Same thing. Instead of gravitational field, change to electric field. Instead of mass, change to electric charge. Is that clear? And then you're going to learn this later on. A magnetic field. So what's a magnetic field? It's the same thing. Instead of the word electric, I'll write down the word magnetic field. Okay, so magnetic field is also the same thing. It's a region in which what do you call that? Pole. Pole, yeah. A pole experience a force. Okay, so I'm just linking these three things together. So all you need to do is just remember this concept. And then it applies to the three things: electrical field, electric field, and magnetic field. They are all a region where the mass or charge or pole experience a force. Is that clear? So it's a place. Okay, it's like a place, okay, where whatever they're talking about. In this case, it's magnetic pole. Sorry. So in this case, I write down magnetic pole, which is can be north or south pole. Experience a force. Understand so far? Okay, so for part C, if you are clear what I'm trying to do, trying to link with the gravitational field and magnetic field, they are all similar. Just change the few keyword. Okay, they are basically the same thing. Just changing a keyword. So if you understand part C, give me a yes reaction. Okay, thank you everyone. Help me clear your reaction. Thank you, thank you. Okay, for part D, you're going to learn this the first time around. But same thing, I want you to imagine a point charge can be the same as a point magnetic pole. Okay, so in this part D, we are talking about a point charge or isolated point charge. Okay, what does this mean? So for example, an isolated point charge can be a positive charge or a negative charge. I repeat myself again. This is a isolated positive point charge. This is an isolated negative point charge. Okay, so they are not close together. They are not close together. So I just draw a line here. They are not close together. Just treat them as two separate pages. So what does this mean? Okay, this means that, okay, I'm going to draw the electric field. So the electric field goes like this. For positive, the line is always going out of it. Okay, so when you see positive, it's going out. When you see negative, it's coming in. Do you remember? So when it's positive, it's going out. When it's negative, it's coming in. So what does this line means? these lines mean that if you were to put another, in this case, positive charge, okay, everything we talk about is positive but not negative. Okay, because negative will be a bit confusing. For example, if I put a positive charge here, okay, it will follow the direction of the line. So where will this positive charge go? You'll go this way. You'll follow the field. Understand? And does this also agree about light charges repel? Does it make sense? Does it actually tells you that light charges repel? So the electric field, okay, electric field means if I were to put a point positive charge in the field, that will be the direction that the point positive charge will go. Understand? Can you see here the positive test charge? So the positive test charge is the blue color thing that I draw. Okay, so the electric field is where I put a blue color thing here. This blue color thing is a positive test charge. If I put it there, you actually go in the direction of the field. So the red color line that I draw out is the electric field. So there's a force that actually move it this way. Understand? Likewise, if this is a point negative charge, if I were to put, let's say the same thing, this positive test charge, this positive charge at this point, it will follow the line in that direction. And does this make sense? Does it actually tie in with point B, where you have unlike charges, it will attract. Okay, it will attract. Okay, so if this negative doesn't move, this is the electric field. Okay, this if we put a positive charge here, you'll move in this direction. Understand so far? Okay, if you understand, give me a yes reaction. Oscar, how are you? Okay? Okay, I will just stop at E in this learning outcome. Then I'll show you all the notes. Okay, before I continue, I know that all of you except Yu have learned this in school. Did I actually help you all understand better, or this is already what you already know? Give me some feedback. Give me some feedback. Is this something that is useful? What I'm sharing useful? I'm trying to tie things down, try to make you understand better, or you already know already? Give me some feedback. Oscar, your B means what? I don't understand your B. You're giving a score. So Chelsea already know, that's why. Okay. So your school teacher actually also share what I share with you all, not just going into the topic straight, right? Yeah, so it's a revision. Okay, let me go to the next part. Hey Oscar, I see you haven't explained to me that you give me a B means what? You give me your assessing me, right? Is that my score? A B? Okay, I'll just for this syllabus, I will just stop at E. Okay, so we're talking about two isolated point charge. The two charges can be unlike or like. Okay, so I just put unlike first and like. Okay, unlike there's only one scenario, 1 plus and 1 minus. Okay, and then earlier on, let me just draw here. Plus is the field is all going out. Minus is all coming in. So when I put a plus and a minus together, what happened? You know plus is all going out, right? But when they are close to each other, you'll no longer be going out straight. Okay? Between plus and minus, you know that you'll go straight to the minus. What happened to the one coming out here? Okay, you go like this. Okay, you all go towards the minus. Okay, it's no longer going out straight. It's actually influence going to the minus. Okay, then from here, it's just a field going out. Then here, come in a bit. Okay, so this is the electric field pattern between two unlike charges. And let me repeat again. These lines with the arrow are the electric field. What does it mean? Okay, what does it mean? It means that if I were to throw if I were to throw a point, positive charge anywhere in the place, okay, anywhere in the place, it will actually move in the direction of the field. It will move this way. Yeah. So if I put a positive point charge here, the field tells you how this thing will move. Understand? Okay, so now we go to the light charges. So I'll just give an example of actually there's two patterns, 2 plus and 2 minus. So how does it look like? Okay, so for 2 plus, you know that the line will all go out. Okay, you know line will go out. So this one definitely will go out. But how does the rest of the line look like? Okay, how does the rest of the line look like? Okay, so in this case, on the left here, it will not go all the way straight and then join into the right one. Okay, so what actually you'll see things like this. Is that clear? Okay, so you see things like this, and then from this pattern, you know that they are blocking each other. They are not going to come together. They are going to block each other. Is that clear? So same thing. This arrow, the line, the arrows are the electric field. It means that if you put a positive charge there, you'll move in the direction. Okay, then right in the middle, there'll be a neutral point. Right in the middle here. This point that I draw here right in the middle, you put a positive charge there, you'll not move because it's right in the middle. Okay, it's a equilibrium point. But anywhere else, the positive charge will actually move in the direction of the field. Clear? Okay, same thing for the two negative light pole. Same drawing, but the arrow is opposite. Okay, same drawing. Something like that. Okay, and one thing that you need to know is the line should never cross. So there's one line that I cross, is wrong. For these two lines cross, I shouldn't do that. Few lines shouldn't cross each other. Okay, and it's all going into the negative. Okay, so the pattern of the two negative is the same as pattern as the two positive. Just that for positive, the arrow go up. For negative, the arrow comes in. Okay, up to this point, are you all clear? Okay, if you are clear, give me a yes reaction. Even your camera, okay? All right. Okay, I'll just stop at this syllabus here. So I was trying to explain this topic to you. Then the last 4 will be a bit more complicated. I'll use the notes to share. You want a break? If you want a break, give me a yes reaction. You don't need a break, give me a no reaction. So 3 of you no reaction, 3 of you have a reaction. Okay, go for a 1 minute break. Be back by 8:37. Okay, so this topic is static electricity, is electrostatics. So we will talk about light charges repel and light charges attract. Okay, we also learned that the unit, the SI unit for charge is Coulomb. Okay, capital C, where you spell the unit is small c. And then how are insulators? Okay, it's not possible to electrostatically charge conductors. I repeat myself again. In this case, we use the word insulator is because for conductors, okay, electrical conductors like metal. I repeat, so the opposite of insulator, right? Opposite of insulator is electrical conductors. Example, metal. Okay, you can't make metal electrostatically charged by friction. The reason is matter itself, they all have this thing called free electrons. Okay, the electrons are not free, the electrons are free moving. Okay, so you can't, the electron on the conductor can move all over the material. So when you try to transfer electron, like remove electron or you add electron to it, it doesn't make the thing more positive or more negative. Okay, because a conductor itself has free electron, you will just take in, if not they give away. It doesn't make the whole thing easily charged by itself. Okay, so for insulator, you can charge them up by friction, okay, by transfer of electron. Okay, because when you transfer the electron itself will not be able to move freely, unlike a metal where the electron can move freely. Okay, so when the electron you transferred are not able to move freely, when there's excess electron, is negative charge. When there is lack of electrons, it will become positive charge. Is that clear? Okay, so I give an example. You look at this glass rod and the silk. Okay, if you were to look carefully, because they are all neutral, you never do anything to them, the number of plus on the glass rod is the same as the number of minus on the glass rod. Clear? Same thing. The number of plus on the silk, in this case, you can see there are 5 pluses, and the number of minus on the silk is the same. Is the same. Okay, so plus actually is the proton in the material. The negative is the electron around it. Okay, so before rubbing, both of them are neutral. They have the same number of proton and electron. Okay, then you start to rub. Okay, you start to rub. Okay, some material would, when you start to rub, right, you will love more electron. Okay, some material they don't like electron, they'll lose electron. Okay, so in this example, okay, how to remember is not easy, like you have to memorize. Okay, but I for O level, they'll roughly tell you which one become more charged or less charged. Okay, generally don't really need to memorize different material, which one is more positive light or which one is more negative light. So for this example, when you use the silk to rub the glass rod, they are both insulator. They are both not metal. So they are both insulator. Okay, so at first they have the same number of positive and negative. And one thing you need to realize, proton always stick to the material. The proton will not move. So on the glass rod, there are 5 proton here. After rubbing, the plus still remain there. It's not the plus that move, it is the electron that move. Is that clear? So when you rub them by friction, okay, you're actually trying to charge them. Okay, so when you're rubbing them, what's happening here is you are actually disturbing the material. Okay, so when you rub a glass with silk, okay, don't memorize which one actually will go where. Okay, but in this example, you can see that the three electron here jump to the silk. Can you see that? So after rubbing finish, okay, the glass will have 3 less electron. The silk will have 3 extra electron. Okay, so the glass rod will become just like your chemistry, like your anion and cation. Okay, in this case, it's something similar. This will become positively charged, and your silk will become negatively charged. But it's not the same as your chemistry, but the idea is the same. In chemistry, when you put cation and anion together, that is an ionic bond. But this is not ionic bond. Okay, this is not an ionic bond. What's happening here is it just transfer a little bit of the electron from one material to the other. Okay, so the glass rod lose electron, it is positively charged. The silk gain electron, it will be negatively charged. Understand? And then you learned before in earlier topic, or in lower secondary school science, electrical insulator or thermal insulator. Why both of them are bad at conducting electricity or thermal energy? Okay, it's due to their electrons are not like metal where it's freely able to move. Okay, the only reason electrical insulator do not conduct electricity is because the electron are not freely able to move within the material. Okay, so for this part, do you understand? You have to hear. If you understand, give me a thumbs up. Ryan, Oscar, Chelsea, are you okay? Ryan and Oscar. Oscar, are you there? Okay, so we talk about principle of electrostatic. Then all this induction thing, we will talk about it next week. Electric field, we talked about it already. Okay. So this one we'll talk about it next week, but let me just talk about the principle. Okay, the principle, we'll talk about it next week as well. Okay, so this one, we'll talk about it next week. I'll just talk about the field and the force. Okay, and then we'll go into touch, then we'll revise a bit of thermal property of material. Okay, so just now we mentioned about electric field. Electric field is a region where an electric charge will experience an electric force. Okay, you all learned this before. So electric force means what? Okay, electric force can be a positive, it can be attractive or a repulsive force. Okay, where charges exert on each other. So when you see here, light charges repel. If this one arrow is the force that's moving away. This is the electric force. Okay, electric field will be the region. This whole region, okay, is the electric field. Then electric field line is this line that you draw, the electric field line. Okay, so the arrowhead in the electric field tells you the direction of the force that will act on a small positive charge. Okay, this I actually explained earlier. How many of you still want me to explain one more time? So I put a positive charge here. This arrow tells you that this positive charge will move this way. Understand? Okay, so electric field is a region. So this whole thing is a region. Okay, so when you put any charge inside that, this whole region, when you put a charge inside, you actually experience an electric force. Because this plus give you a repulsive force, this minus will give you a attractive force. If you were to put a positive charge inside the region. Okay, so far? Okay, and then we also talk about a point positive charge. This is the field line. A point negative charge, this is the field line. When you put two positive together, it look like this. And then instead of 2 point charge, you put two bars that is different charges, your electric field line look like this. Oh yes, one more thing that I did not explain to you earlier is when you learn about magnetic field line, everything is the same. Everything is exactly the same. Okay, instead of plus, you change to north. Okay, so north pole, like two north pole will repel. Same thing, the plus become north, the minus becomes south, they will attract. Okay, then magnetic field is a region where a magnetic pole experience a magnetic force. This I explained to you earlier on. Same thing, if you have a north pole here, your field line should all go out. If you have a south pole here, your field line will all come in. So if you were to put a point north pole, okay, at this point, it will go in this direction. Exactly the same thing, your plus change to north, your minus change to south. Okay, likewise, in a magnetic field lines, for if you put a north and a south together, okay, This is how the magnetic field line will look like exactly as well. Same thing, no different. So for example, if I have a magnet down here, north and south south and north. Hold on. Yeah, south and north. The field line will look like this. Is that clear? Or if I have this magnet here, but this is north and this is south, exactly the same, the field line will be the same pattern. Okay, so what you learn today in drawing the field line in the definition for electric field, electric force, it will be exactly the same thing for magnetic force and magnetic field. Okay, so when we go into the magnetic topic, it will be exactly the same. But instead of charges, you change to pole. Clear so far? If you understand, give me a yes reaction. And then it will be, and then yeah, then that's all for today for this topic. All right, so I'll spend the next 10 to 15 minutes to just go through thermal property. Yeah, this is the one. Okay. Any of you, especially Ethan, this topic is also quite heavy. Any part of this topic you want me to revise? Don't tell me the whole topic. Which part you want me to revise? You want me to talk about heat capacity, latent, and so on, calculation? Have you seen the topic that we went? Have you seen the videos I sent you? Have you watched the video? Okay, so if you're talking about calculation, there's only two parts. Okay, there's only two parts. Okay, so let me just explain a few things first. Later, so many videos later you watch it, got time. Oh yeah, but you can fast forward. Okay, let me share the whiteboard. Okay, just let me talk briefly the concept. I will not go through example anymore. If you want to see example, I'll give you some link. Last week, right? You go and see those past year paper question. You can try yourself. If you don't understand, you listen to the explanation. Okay, can you do that, Evan? Okay. So let me just draw the temperature time graph. So if I were to supply heat, okay, if I supply heat, let's say water, I use water as an example. Okay, what I'm drawing now will apply to most material. So if I were to supply heat, if I heat up something, okay, so this part where the temperature goes up, this part here is the solid state, okay, solid state. Okay, so I supply heat throughout, okay, I supply heat throughout. Then this part will be the liquid and this part will be the gas. So generally, if I were to heat something up, the temperature should go up. Yes or no? Or if you understand this, if I were to heat something up, the temperature should go up. Okay, but there are exceptions. If you look at this graph, the two exceptions is here. Hold on. Okay, look at this graph. The two exceptions is down here. This part here and this part here. Can you see? So from at this part here, let me show you what's happening. Okay, so this part here, maybe just draw. I got a lot of cube of ice. Okay, then I actually supply heat. So these are all ice cubes. So when you supply heat, once you reach the melting point, so this is the melting point. So this is the melting point, and this is the boiling point. Okay, so at the melting point, okay, this whole thing that I'm going to talk to you is the same as the boiling point. So here will be what happened. Here will be this part here. Will be when you're boiling the water. Okay, when you're boiling the water. Can? Okay, so this phase we call it melt. This phase we call it boil, where there is a change of state. Okay, so when you're melting a solid, you're supplying heat. Okay, when you're supplying heat, at the melting point, the solid ice will start to melt to become liquid water. Okay, I'm just revising the concept. I haven't gone into the formula and the calculation. So at this phase here, the name for it is called melt. Okay, this phase here, the name for it is called boil. And these two things, melt and boil, is the point or the phase where the object changes state. I repeat, the melting process and the boiling process is where a material change state. So even though you are still supplying heat when your ice were melting, okay, so the solid change to liquid at this point when it's melting. But the whole process, you're supplying heat, but the whole thing, the temperature remains the same. Clear so far? What I'm saying is actually primary school science. Likewise, at the boiling stage, even though you're still supplying heat, you're giving it a lot of heat, a lot of fire. But when you start to boil, the temperature remains at 100 degrees Celsius until every single drop of liquid has changed state to become gas. Clear so far? If you understand, give me thumbs up. Just you understand this primary school science. Okay, so let me go into a bit about physics already. The sec 3 physics. Okay, so this is the part where it's flat. So you already know this part. You put one side first. I'm going to talk about the part where it's not flat. So I'm going to show you it in green. So this part in green, this part in green, this part in green. So these three parts that I draw in green is where if I give it heat, the temperature go up. If a liquid I give heat, the temperature go up. Same thing. For a gas, if I give the heat, the temperature go up. You only may give you an example, like your metal spoon. You heat your metal spoon, your metal will still remain metal, your spoon will still remain metal, but the temperature go up. Make sense? Or you heat up your coffee. Okay? It still remain liquid, but the temperature goes up. Or if you heat up your room, you put a heater in your room. Okay, your oxygen in the room, the temperature will just goes up. Okay, if there's no change of state, when you supply thermal energy to the material, the temperature will go up. Clear so far? Okay, so I'm going to talk about the first formula. Okay, so I actually went through the basic. So the green part, where there is no change of state, the formula we use is this: Q equal to mc theta. What does this mean? Okay, let me explain. Then you go and see whether does it make sense. Q is the amount of energy. The amount of energy supplied, in this case, thermal energy, the amount of heat. Okay, the amount of heat energy required, okay, required to raise 1 kilogram of mass by 1 degree Celsius. Okay, so far? I repeat myself again. This formula here, Q equal to mc theta, it means that the amount of energy, thermal energy required to increase 1 kg of mass by 1 degrees Celsius. Okay, so what is this small c here? This small c will be your specific heat capacity. Okay, let me find out what's the value for water. If I'm not wrong, it's 4,002. Let me just go and Google first. Okay, I don't give you the exact value. I'll give you the estimated value. Okay, so for water, okay, every material is specific. Okay, but for water, this value is for about 4,002 joule per kilogram degree Celsius. Okay, so far? So every pure material has this specific heat capacity. So what does this mean? So it means that for water itself, for 1 kg of water, for 1 kg of water to increase by 1 degree Celsius, you need 4,200 joule of energy. Clear? Which is the same thing as what I'm trying to say here. This amount of energy required to raise 1 kilogram of water by 1 degree Celsius. So specific heat capacity is the fixed value of the material, okay, the fixed amount of energy required to raise 1 kg by 1 degree Celsius. Okay, did I try to make you appreciate this thing better now? So when you need to memorize this formula, you must understand what it actually means. So Q equal mc theta basically just tells you that how much energy you need to raise the amount of mass by how much temperature. So if you have 3 of these values, you can find the last one. Clear so far? Now, the next thing, the red color part. The red color part, there is no temperature. Can you see where the temperature is fixed at 100 degrees Celsius? Or when it's melting, the temperature is fixed at 0 degrees Celsius. Okay, so for this part, the temperature don't change. So it's the same formula as this, but without the theta. Clear so far? So the formula when it is changing state, how much energy you need the water to change state will be Q equal to ml. AQ ml. Likewise, this is Q is the amount of heat energy that you need to boil water. Okay, the amount of energy you need to boil water to change the state. M is the mass of the water. Okay, 1 kg of water. And then this L will be the specific latent heat. Okay, this specific latent heat can be latent heat of fusion or vaporization. So for boiling, it becomes a vapor. This L will be specific latent heat of vaporization. Then for melting, it will be the other one. The L will be the specific latent heat of fusion. Clear so far? Okay, so let me go and Google what is the latent heat of water. Specific latent heat of vaporization of water. Okay, let me give you a value. So for water itself, it is, wow, a lot. 334,000 joule per kg. Okay, so for water itself, it is about 336,000 kilojoule per kg. Okay, what does this value mean? Okay, so every material there's a fixed value. So the specific latent heat of vaporization of water is 334,000 joule per kg. So what does this value mean is that to actually boil 1 kg of water, for every kg of water that you want to boil, you need 334,000 joule of heat energy. Is that clear? Okay, likewise down here, melting. To melt, for every 1 kg of ice that you want to melt, you will need 336,000 kilo. Sorry. I'm sorry, this K remove. You need 336,000 joule of energy to melt every 1 kg of ice. Clear? And then for water, what does this mean? For every 1 kg of water, to raise 1 degree Celsius, you need just 4,200 joule. So can you see, for a state to change state, it takes a lot of energy. Whereas to raise the temperature, it doesn't take as much. So if you actually boil water at home, okay, as a temperature from room temperature to 100 degrees Celsius, it can take maybe 15 minutes, for example. But for all the water to boil to become steam, it will take maybe another 30 minutes for all the water to be boiled. Is that clear? Because changing state needs a lot of energy. Okay, so today when I explain like this in your exam, they would like to ask you how much energy is needed to raise the temperature of this or to raise the temperature of that. Or in O level, they may be a bit more tricky. They give you two material. When they put them together, what will be the equilibrium temperature? So you must say that the energy, okay, the energy used to raise the temperature for the first material will be the same energy for the second material to lose the temperature. So you can use Q equal MC theta equal to Q equal MC theta. Because the energy gain of one material will be the same as the energy loss in the another material. All right. Then from there, you try to solve the problem. But the concept is like this. Clear so far? Okay, so if you ask me, Q equal to ML is for specific latent heat. So is there a formula for like only latent heat? Okay. Yes. Even when you talk about latent heat by itself, latent heat, it is the Q. It's basically, what does latent heat mean? Latent heat means how much energy you need to change the state of the material. So Q actually is the latent heat. But the L here is the specific latent heat because it is a fixed value for every material. It's just like density. A density of gold is always fixed. It doesn't change. Clear so far? But the mass of gold is different everywhere. Likewise, to boil water, how much energy to boil water is different. Whether you have if you have 1 liter of water, the amount of energy to boil water is different with 2 liter of water. So this latent heat will be just a total heat you need, okay, to boil the water. Understand so far? Then, if I don't understand your second question, maybe you look at some practice example and then you try. Let's see whether you understand better. Okay, likewise for this formula, maybe for this example, it's harder to understand what does latent heat means. Okay, but in this formula, Q is a meaning, the Q here is latent heat. Okay, let me explain using this one. So this small c here is the specific heat capacity. Okay, and let me show you. Then there is another term that you see sometimes in exam, just call heat capacity. So this M and C, we can change it to a big C. It's called heat capacity. It's the amount of energy to change the temperature of that material. You don't care about the mass, okay, of that amount of water by 1 degree Celsius. That's so far? So likewise, if you understand what I'm trying to say, it's the same thing. This ml is the amount of energy needed to boil the water. So this heat capacity means the amount of energy required to raise the amount of water by 1 degree Celsius. You understand the linkage now, the similarity here, which I hope you understand what does latent heat means now. So I use this to explain heat capacity without the word specific means M times C, which is the capital C. And this capital C means that the amount of heat that's needed to raise the temperature by 1 degree Celsius for this amount of water. And this amount of water is not 1 kg. It's the amount they're talking about for that example. So it's not specific. So this big C is different for 1 kg of water and 2 kg of water. But the specific heat capacity is the same for all water, regardless is it 1 kg, 2 kg, or 100 kg. Clear so far? So this specific heat capacity and the specific latent heat is a fixed value for a pure material. Just like density. How do you tell whether this material is pure gold? You check the density, not the mass, not the volume. So specific heat capacity and specific latent heat is a fixed value for each material. Whereas this big C or this big L here, this ml here is actually the big L, which is specific, which is latent heat. It's like the mass or the volume of water. It can be different for every scenario, but specific heat, latent heat, and specific heat capacity is always a fixed value, just like density. Is that clear? So is my explanation like this useful? They actually make you understand the idea of specific value for your. You remember me saying this during the lesson last year? How many of you remember? Or you actually, when you are listening, this doesn't register with your. Okay, so today I talk about 1/2 of static electricity, and I also revise a bit of this specific heat capacity thing. Okay, so what I want you all to do before you all go is to tell me, give me a rating between 1 to 10, where 10 is good, the best, 1 is the worst. Okay, on the topic of static electricity, and then give me a rating of how much of you does it help in this so-called revision of specific heat capacity. So give me 2 numbers, and then last question, 1 thing that you learned today. Okay, if you have any more questions, you can stay back. If not, after you give me the answer for the 3 questions, once I call your name, you may leave. So I repeat, give me a rating of the static electricity explanation, a rating for the heat revision, and finally, 1 thing you learned today. Ryan, I don't understand. Go and try again. I still don't understand your thing, Ryan. Even you say that when temperature increase, state does. Okay, when the temperature change, when you supply or take away heat, right? And if the temperature were to change, it means that the state doesn't change. Whereas when your state changes, temperature does not change. So your first statement is you need to change. The second statement is correct. Oscar, you may go. You got no other question. Thank you. All right. Thank you, everybody.